All right, hey everybody. So I hope everybody has been having a good time so far. So my name is Minh, and I was from Fortinet, specifically the FortiGuard division that perform security research for the corporation. And before that, I actually was from Palo Alto Networks. So I was a senior malware research engineer over there. And so before that, and I worked for North Carolina State University as a researcher there, where I also earned a master's degree in computer science in 2011. And so recently I was very honored to be named one of the top 100 security researcher by Microsoft. So they just released the list on Black Hat on the 9th of August, if I remember correctly. So some of you mentioned that they may see me in Black Hat, and actually not, because I was not at Black Hat, but maybe they see my name in the plaque they put in there. So I was number 56 on the list. So just before we get started, a quick show of hands. How many of you use Android as a smartphone? Oh yeah, quite a lot. That's what I'm expecting. So you come to the right place. So in this talk, I will introduce some enhancement to perform malware analysis on Android and improve the detection rate overall. So let's get started. And so first, let's begin with the motivating example. And then afterward, I will talk about the architecture of the system. I will also share some of the results that I can share. For obvious reasons, I cannot touch some of the topics. So yeah, that's the deal. So and then afterward, I will show some future research directions, so you can perform additional work on that as well. So let's come back to the topic at hand here. So in the corner, you can see this is a mature malware. And I took this screenshot because it represents many key points that I will introduce in this talk. So first of all, they are mostly corrupted. You can see over here. And at the same time, they also use social engineering attacks, in that they trick the user into believing this is a legitimate app. For example, this is a Flash. This is a Deutsche Bank, which is the biggest bank in Germany. So there are two main points that you can take note and realize that actually in other kind of malware and in other benign applications, they never actually experience this kind of behavior. And so if you run these through the normal malware detection system like Palo Alto Wi-Fi or whatever, then it may not actually detect this thing because for one thing, it's corrupted. So if you actually run it inside the dynamic analysis system, the system cannot run this, so it will basically return benign to minimize the chance of false positive. Because actually, if you work in malware analysis system like I do, then the most common complaint that you will get from the customer is that they will say that you have too many false positives, so their SOC cannot handle so much false positive requests. So the number one complaint the customer will give you is that your system still has high false positive rates, so they will want to reduce the false positive rate of the system. So if you run this through the dynamic analysis system, for example, it will return benign. And so, but at the same time, the customer also have high expectation in that they want to be consistent with what other systems are saying, because their boss may scan that thing through Symantec or whatever, and that solution return a malware verdict. But the dynamic analysis system actually return benign. So there is a discrepancy there, and the customer will feel nervous and complain. So there is a room for improvement in terms of detecting that kind of sample. And also, the malware can be generated by many kind of kits, and typically there are lots of variation there. So if they all follow the same thing, then your system cannot detect them. So that's the main motivating samples that motivated this research. And in a nutshell, that's the reason I came up with this idea to improve the malware detection further. So let's get right to it. So as I mentioned briefly, the first point is that they use obfuscation. So if you pay close attention here, like a legitimate application here, they use very legitimate names and very formal as well, like mobilesecurity.symantec.com. So it's pretty much like a domain name, and which is starkly different from the obfuscated names like you can see below here. So it's so intuitively, as a human being, you see this and you realize they are different, and the second one has a much higher entropy than the first one. So this pattern actually is very generic, because if you look at the IPA packages, which is the package format for the iPhone, and then the Mac, the package is called the bundle, which is basically another terminology, but basically it's the same thing. It's also a zip archive. And you see the pattern of the name also very formal like this. So actually it is significantly different from the obfuscated name here. So that in a nutshell is the key insight number one. So you can use the enemy strength against them. So that's the number one I would like to mention. And so the number two is this one. Okay, hold on. All right, here. So this is the second pattern that I noticed that, for example, when you look at those samples here, those are actually legitimate samples you can find them in VT and various open source, the threat intelligence sources. They actually use the same icon as WhatsApp over here. So obviously they try to trick the user into believing that it is a legitimate application. The same way that on the desktop they can use PDF icon or Word icon, whereas actually the main file is executable. So it's a PE executable, not a PDF file or doc file. But the same pattern over here. So actually this is very generic and can be applied to various other systems as well. So then the second insight is that they shouldn't use social engineering attacks like this. So if you are truly legit apps, you just have the normal name, or if you are obfuscated app but still benign, then you shouldn't try to use the application icon of various legitimate apps. So in a nutshell, it sums up the point here, and the point can be highlighted in many other apps as well. So in my experience, I have found the application use this kind of legitimate icon like F-Secure, which is a security company, or Amazon, or Facebook, or Firefox, or Postbank, which is another bank in German, for example, or Viber over here, which is also popular. So based on that, you can see that there are two key insights that you would like to detect, but at the same time, they also pose the challenges, so how to detect them. So here's how. So here's the reason I came up with this and how I solve these challenges. It's called machine learning. So let me give you a kind of machine learning 101 here. So in traditional programming, you basically try to figure out the right rules based on your additional research and whatever, and then feed it the data. Data in this case being malware or samples that you would like to classify. And then your dynamic analysis system over here will try to give you an answer. So it is starkly different from the paradigm in machine learning. Specifically, in this case, it is supervised learning, where you feed it the right answer, which is a training samples with a two label, which is a benign or malicious. So in this case, only two classes. So there are two over here. And then even you feed it the right data, and it even train and output to you the rules. And so in terminology of machine learning, the rules is basically a models, and the output is a model files that can feed it into the machine learning again. So the next time when you use in classification phase or prediction phase, you feed it a sample, even yield to you the prediction that you will take, for example, benign or malicious. So to solve this kind of machine learning issue that I already mentioned, which is supervised learning, and specifically to classify images like this, and I use a neural network, specifically a special kind of neural network called deep neural network. So to give a very, very brief introduction into neural network, you can look over here. So there is a series of neurons called the input. In this case, each input in my system will map to one pixel on the icon. And then there is an output over here. In this case, it's not two output like malicious or benign, but the number of output will depends on the number of applications you would like to classify. Obviously, you need to classify into each of this class individually. So each of these is actually one class and needs one neuron to classify that thing. So intuitively, you can see that what the neural network actually works is that it uses the input neuron to absorb the data and then feeding into the hidden layers in between here. In this case, you only see one, but actually for the neural network to perform optimally, you need many more neurons over here. And then it will change on the weight and biases inside the neuron. And then eventually, when it feeds forward to the output, and whichever the output has the highest score is the one that it detects. For example, if the malicious here has highest score, then basically that is the output of your model. So that pretty much sums up everything about neural network. And so let me put it all together here. And with machine learning, we can do two things here to classify package names. We use the n-gram model, and to classify images, we use a neural network. And for that, we use the open source framework from Google called TensorFlow. So I performed this work last year, at the end of last year. But right now, then Google has already introduced a newer version. So the newest version is probably 1.7 or 1.8, and also on top of that, they build the additional better higher level API called Keras. But in this work, I use the lower level API where you can specify a lot of parameters and hyperparameters and all that kind of thing. So specifically, it's called Inception. Inception is one of the contributed model from the researchers, and then Google incorporated that thing into TensorFlow, and it belongs to the contrib namespace. And then later on, it has been merged into another framework called Slim. So it has many additional properties like distributed learning and whatnot. So if you are interested, you can search for this model name in GitHub, and they will give you the full source code of this in Python, and then how to use it, and on top of that, I will give you a brief introduction on how to use it here as well. So what is special about Inception is that it has a Inception block, and you can see over here, each of these is one Inception block. So there are 7 of them, and actually this is still very high level because each of the smaller block over here have many functionality, like for example convolution or pooling or concatenation, and then fully connected. And the final layer to classify is called softmax. And then the first layer is called input layer over here. So actually they are very, very deep. That's why they came up with the name deep learning. So that's basically a neural network with very deep layers, and they call it deep learning and become a buzzword recently. So the reason we choose this model instead of other model like GoogleNet or VGGNet is because it has lower computational cost. Why this is important? Because when you do the training for this model, you only need to train lower steps than in bigger model, and it takes even then it already takes a long time to train. And even more importantly, in production you would like to have higher throughput in terms of classifying sample. So your feature is just one feature on top of many features of your malware analysis system. So you would like this feature to complete in less than 10 seconds to classify a sample. So that's the reason we chose Inception for our system. And for our POC specifically we use Inception version 4. So that's the reason. And so with that, I will go deeper into the architecture of various parts of this system. So first of all, to train the neural network, and specifically in this case, it is supervised learning. So you need to first building your input. So in this case, we need to build a corpus of icons, and then afterward, after you have already labeled the icon, you can feed it into the neural network at the training mode, and then afterward, it is spitting out a model file for you, and you need to perform the evaluation based on cross-cutting of the sample, and then to test the loss and test the goodness of the system. And then after you have a few iterations like that, and it's good enough, and you have the model file for production. So that's at a very high level. In the following slides, I will show you additional details of those steps. So this first step is to build a proper corpus of icon here. So the first challenge is how to crawl for this icon over here, because it can come in various resolution and names and all that kind of thing. So in this case, we found out a Chrome extension, and based on that extension, we modify the code and perform the crawling and save to the disk. But that's not all, because you also need to label this properly into individual classes, because obviously the machine doesn't know which is a tag, which is a label of each of these icons. So actually, this is a very human-intensive task. And we would imagine that in production to train more classes, like 1,000 classes, for example, you will need some good human sources, like Amazon Mechanical Turk is a good source to outsource this human task into the outside world and then get back the label for you. So instead of you having to do it yourself. So that's one way to do it. In this POC, then I do it myself, but in production, in large scale production, we need to do that. And so at the end, then you have a folder, each corresponds to one class, and then it comes to the second stage, which is the training for this neural network. And so TensorFlow, they already have the code to convert that thing into internal format. So you can do that. And then training the neural network is very intensive. So in that case, I couldn't spend the time to train on the entire Inception v4 from scratch, so I only trained a few last steps, last layer of the neural network for classification. And for the softmax layer, which is the last layer, I only need to train 3,000 steps, and that's already good enough. And then after it has produced a normal file with the optimal weight and biases for neurons, then you can go ahead and do the cross-cutting evaluation on various samples. And then, all right, so now we come to the second challenge, which is the training of the language model. For this language model, it's challenging because you need to basically classify between the malicious sample and the non-malicious sample, which is which looks significantly different and easy to tell from the human point of view, but not easy for the machine. So you need to find the data sources to train your model, and then the model will tell you the truth. So at that point, it becomes kind of an oracle that you can just feed it the data, and then it will spit out the label for you. So in this research, and we found out that we can use Alexa and Majestic Million, which has a big corpus of words. So you can use to that as an approximation for the reality of benign words and application. And then for labeling, then you also need to somehow find the ground truth, which malware sample, which class name is already known to be malicious, which is known malware, not malware. So for that, we use VT. And so after training the model and perform this testing loop over here, that's not good enough, and you need to come back at the beginning. Then we finally figure out that the n equal 3 yield the best result. We already trained this with n equal 2, 3, 4, 5, and we found that 3 yield the best result based on the testing corpus. Alright, so here, let me put it all together. And so it is the final workflow after you've done the hard working part, which is the training of the model. Then you can put that model to good use, and then it yield back the result to you. So this is the final workflow in the production system. But also keep in mind that the whole system here is just a subsystem on top of a bigger system to perform the final classification of malware. So that's why it is very important that you need to have high performance. So you need to pass in to get out the package name here, and then you classify by the language model first, because as you know, in package filtering or in malware filtering or whatever kind of filtering, you put the cheapest and highest performance filter first, and then each additional step is more and more expensive. But at the same time, you already know whether it's benign or not, quite confident already. So the number of samples that we get to the last step, which is more expensive, will be also the minimum. So that's how to optimize the filtering stages of the system. So that's why the extracting icon on that kind of classified by deep neural network actually at the bottom over here. This is the most the highest performance step all the way at the beginning. So that's how this step of the system works. And with that, then let me show you the result here. For the test set, we have more than 300,000 samples from VT. And as you can see over here, for 2 gram detection, then you have the detection rate of like this. So the false positive rate is actually still quite high. It's 11% over here. And for the 3 gram, then you have even, for the 3 gram, then eventually you have the detection rate only, the false positive rate is already like this. So it's the best performance of the entire system. And for the 4 gram detection, then it's worse off again. So that's why we decided to settle with the 3 gram. And so, let me sum up the result of the POC. So the result is that we have better classification overall because, it have additional features to detect this kind of special malware. And at the same time, it has better coverage because, sample can be corrupted, and our system still works because, fundamentally speaking, it's static analysis, whereas compared to other dynamic analysis solutions, they will fail because they cannot run. And they cannot run because so many other reasons, not just because of the sample is corrupted, but as you may know, for example, Cuckoo Droid or various systems only support up to Android 4, but actually right now Android already gone to P or O, so the version number is way higher, and API level also way higher, so they cannot run. So that is one of the many reasons why dynamic analysis can fail. In fact, anything can fail unless the only way to detect malware is to put many things together and perform and enjoy the fact that you have defense in depth for your system, so you can detect many malwares. So effectively speaking, then the detection rate of our system, the whole thing putting together is 99.92%. So that is still have room for improvement there. But the beautiful thing in here is that our false positive rate is below 1%. So our customer doesn't really complain too much about that. So we have more time to focus on other tasks that we have to do, like improve other IPS system or whatever. So you have bigger fish to fry than just this. That pretty much concludes my talk. So I hope I have inspired you that ML is also valuable for malware detection as well. And for future research, and actually there's also a lot of room for improvement as well. Because if you think really deeply about it and look deeply into this, and actually our model is only trained on English data sets, but actually there are many other languages in the world with different kind of entropy between character. For example, in Mandarin, when you romanize Mandarin, you see a lot of X and Y and Z, but actually in English, there you do not actually see that many X and Y and Z. So the frequency and the entropies are very different between Chinese and English, for example. So that's one of the way to improve the quality of machine learning. And also to improve training performance, you can perform distributed learning or training on the GPU. So for the NVIDIA GPU, for example, I cannot tell you the name, but you can perform some so-called dark magic to turn a GeForce card into a Tesla card. So that saves you like more than $1,000 for a card, so to perform training. So that's basically one of the ways to improve the training performance. And I think that concludes my talk, and I'm happy to take any question you may have.
Okay, thank you very much, Minh. Are there any questions from the audience? Okay, do keep in mind that if you do have any questions later on, that Minh will be around, so you can just ask them to him anytime. Thank you again.
Thank you.